So, good morning. My name is Thomas Schulz, and I'm here to start off this beautiful day with all of you with 4 fabulous full papers that will all be related to analytics in science and engineering. I'm looking forward to the 4 exciting presentations, but even more so to engaging discussions about them. So please remember to put your questions on Discord or in the YouTube live chat. So now, without further ado, I would like to leave the stage to our first speaker, Haiyan from the University of Zurich, who will be presenting joint work with Rafael Ballester-Ripoll and Renato Pajarola on interactive tensor-based sensitivity visualization.
I'm Haiyan from the Visualization and Multimedia Lab in the University of Zurich. Today I'm going to present our work, SenVis, an interactive visualization tool for sensitivity analysis based on tensor methods. For a given mathematical or simulation model, sensitivity analysis studies how the model's output uncertainty can be allocated to the uncertainties from its input variables, which can be very useful for model understanding, refining, and simplification. For example, this is an Ebola spread model, which models the reproduction number as a function of multiple variables. And the experts would like to know which variables influence the output the most, in order to intervene the process of the virus infection, and thus in the end decrease the reproduction number. For example, variable gamma1 and psi both appear in the nominator and denominator of this function, thus very unintuitive to tell how much influence each of them contributes to R0. So the question is how to numerically quantify the significance of each variable, moreover, the significance of combinations of variables. Good thing is, this problem is well studied in terms of global sensitivity analysis. And variance-based sensitivity analysis proposed by Sidwall is one of the most widely used methods. It decomposes a squared integrable multidimensional function f into a sum of subfunctions. Each subfunction f alpha only depends on a different subset of the n-input variables contained in alpha. Given the total variance of the function as d, we can split it up into a partition of variances v alpha. Then normalizing v alpha by the total variance d, we get sensitivity indices, or Sidwall indices, as alpha. Notice that for a function with n input variables, there are 2 to the power of n possible subsets of n variables. Thus, the Sidwall decomposition contains 2 to the power of n items. To efficiently manipulate the large set of the Sidwall indices, we organize all the Sidwall indices into a Sidwall tensor, which is a hypercube of size 2 to the power of n. In this format, querying any Sidwall indices is equivalent to manipulating hypercube slices. However, when n becomes large, storing this exponential size dataset can be computationally costly. To avoid the curse of dimensionality, a tensor decomposition method was proposed by modeling the function as a tensor train surrogate. Tensor decompositions are higher-order generalization of matrix singular value decomposition, which can represent high-dimensional data in a compact form, among which tensor train model is of particular interest because of its linearity of dimensionality. Sidwall tensor model uses a sequence of n tensor calls Tn to represent n-dimensional data, except for the first and last tensors T1 and Tn, which consist of 2 row or column vectors. All other tensor calls Tn consists of two slices of matrices. The first slice represents the absence of the variable, and the second slice represents the presence of the variable. In this example, if we take the second slices of the second and last tensor core, and the first slices of all other tensor cores, it will result in the superindex of variable tuple 27. And all the other superindices can be easily computed in a similar way. Moreover, based on the super-tensor tree model, we are also able to compute aggregated indices with very little cost, which result in 4 types of sensitivity indices, as illustrated as color-coded areas for variable tuple 1, 2 in case of a 4-variable function. Different types of indices give us more information about the sensitivity of the whole input variable space. For example, total indices tell us the sensitivity of not only the variable tuple itself, but also all the interactions with other variables. Thus, is often used as the indicator for unimportant variables. Closed index 1, 2 tells the influence from only 1 and 2. If looking at the closed index together with the superindex, we can be clearly informed if 1 and 2 have a very strong or little interaction effect. And the superset indices is very useful when computing the relative importance. Relative importance is our newly introduced quantity, which basically tells us what fraction of the overall effect of beta is actually due to its interactions with variables in alpha, and allow us to break down joint effects into their building blocks. This helps us to distinguish case where beta itself is very important from case that beta is important because its interaction with alpha makes it important. However, being able to compute and store all the superindices does not help us much to understand these indices. When n is small, for example 4, we can still visualize all the superindices in the traditional way, like a Venn diagram. However, this quickly becomes inadequate when n grows. Thus, we developed an interactive visualization tool, SenVis, to help understand and explore the sensitivity indices, which in real applications can be very useful for model understanding and simplification. First of all, a direct display of all the sensitivity indices values is a good guidance for further exploration. And this is achieved by tabular view. 4 types of superindices are displayed in the sortable table, so the user can quickly find out the larger superindices, which in most cases correspond to the more influential variables. The table is organized based on the number of variables, so users can access higher order indices easily in an intuitive way. Notice that the variable column is color-coded in green or red based on the directional covariance, a newly derived quantity that helps to indicate if a variable's influence is positive or negative towards the output. For example, if our target is to increase the output, we can pay more attention on the green-colored variables. Considering the possible high dimensionality of a model and the relatively limited number of effective input variables, we add a variable selection option for interactive exploration. So after exploring and finding out the influential variables from the tabular view, user can further select those specific variables, and then the sensitivity indices of selected variables will be queried and visualized. The purpose of the designed visualization is twofold. First is to directly show the relations of 4 types of sensitivity indices as a generalization of the Venn diagram for large N. Second is to visualize the relative importance quantity to help users dive deeper into the interaction of the influences from different variables. To achieve this, we designed 2 visualization views for the visual analysis of sensitivity indices. Sidwall view encodes the value of each sensitivity indices as bar chart or donut chart. The relations of Sidwall indices and the other 3 aggregated indices are encoded as weighted links. Moreover, the directional covariance is also encoded as color circles together with the label information on the right-hand side of the view, indicating either positive or negative influence of variables. Hovering on any Sidwall indices will highlight those other types of indices that are related with it, and the comparison is also supported by clicking on the interested indices. Interaction view, on the other hand, visualizes the relative importance at linked scatters using a novel hourglass design. All the selected variables are placed as bar charts on the top and bottom of the view, representing set alpha and set beta. Each circle in the middle area represents one relative importance relation between tuple alpha and beta. Users can hover on the circles, which will highlight the circle and its related alpha and beta bars. Users can also click on the circles for direct comparison. If clicking on the top or bottom bars, it will highlight all the relative importance circles that share the same set alpha or set beta. Lastly, by using the filter on top of the view, smaller circles will be filtered out, and users can focus on the most important variable relations. SenVis also supports user-defined models from the model upload functionality in the navigation panel, so the user can upload their own model to analyze the sensitivity indices. Next, I will shortly demonstrate our SenVis system on the Ebola spread model. First, from the navigation bar, we can choose the predefined model. The Sidwall tensor will be built and the sensitivity indices will be calculated from the server side. Then all the first-order indices will be displayed in the tabular view by default. Higher-order indices can also be navigated. Normally, we can just select the variables with large Sidwall indices. Sometimes, like here for the Ebola spread model, we want to study those variables that humans can intervene. Thus, we select those specific variables based on the prior knowledge. Then, the Sidwall view and interaction view will be generated. By inspecting the directional covariance in the Sidwall view, we see that variable 8 psi, tuple 7,8, omega psi, and 2,8, beta 2 psi have the largest decreasing effect on the output. Can we then directly go to apply this information on the model? Answer is no, because we are not sure if there are interaction effects with other variables. What if we increase psi but causes the increase of beta 1? This will eliminate our effort. Thus, we check the interaction view. What we know is beta 1, 2, 3 will increase output, while omega and psi will decrease output, which is what we want. Omega has little influence on other variables, which means if we enhance the effect from omega, those, especially beta 1, 2, 3, will not be affected to add opposite effect. Then, if we check which variables are influencing omega, we can see beta 2 and psi have stronger interaction with omega. Because psi can provide the same effect, we only need to pay attention on beta 2 because its change will heavily influence the effect of omega. In contrast, psi has a very strong interaction with other variables, especially beta 1 had the most interaction with psi. Similarly, we check all the other variables. Beta 3 has no interaction with other variables, thus easy to deal with. Beta 2 mainly affect omega, as we already know, and beta 1 can affect the influence of psi. Lastly, users can also easily upload their own model here and analyze the sensitivity indices. In this work, we developed an interactive sensitivity visualization tool which employs the powerful tensor train decomposition technique to achieve a fast and accurate computation and query of sensitivity indices. The approximation accuracy can be controlled by user-defined threshold. And this method is able to model the whole complexity of a model quantitatively. Please check out our open source project in GitHub, and thank you for your listening.
So welcome, and thank you for this very clear talk. So now actually we have two of the authors as a panel to answer all your questions. And maybe I can start with one. So of course, this is a very timely and relevant system to allow us to determine how can we limit disease spread. It's a very important task. Now I am wondering, what do you consider to be the limit in terms of the number of variables that your model would be able to, or also the visual interface would be able to handle?
Actually, this is a very good question. And also, we didn't mention this in the talk because the time limitation, but we actually pointed out in our paper, especially in section 7 discussion. So our system can deal with models within 10 parameters in a very short time. So you can achieve a very fast interaction and exploration. And within 30 parameters, we can still deal with it. But if you increase even more, then the problem happens in the front end visualization, because then we have like hundreds of thousands of millions of subsets, as you know. So then we got a little bit problem. But have to point out that our backend can still deal with even large model, like you can exceed like 30, 40, we have tested, there's no problem. So yeah.
So the current limitation, you would say, is in the visual design. So if you wanted to go for a larger number of variables, the tensor train would still be able to handle it.
Yes.
But you might require an extension of your current user interface.
Yes, yes, exactly.
Let's see, I'm going to check the Discord. So there's lots of applause for your very nice presentation.
Thanks.
I'm wondering about the accuracy of this tensor train approximation. How important do you think is the role? Because somehow this allows you to make the whole problem computationally feasible doing this approximation. So how crucial is it to get this parameter right?
Maybe I should take on that question. Yeah, so that has to do mostly with the backend, with building actually this compressed representation, and it's a compression problem. In all our cases, we were able to build a tensor with sufficient accuracy, where sufficient means 10 to the -4 or -5 in terms of relative norms. It's basically having a very low root mean squared error, and that was well enough within limits of convergence, meaning that the Sobol indices wouldn't change anymore. So we build the compression as good as it was needed, as large as it was needed to ensure that the indices were faithful. Of course, there's no free lunch, and you could have potentially some models that are very nasty to compress, right? And you can never compress everything, right? There's always going to be something that resists. But for all of our applications, we never hit this problem. It was always feasible to store it in something that fit in the back end and was able to compute the Sobol indices fast enough.
And for this approximation, does the order in which you put the variables, does it play a role for how compressible it's going to be?
Yes. So it's a combinatorial hard problem. And there's always you could always find a better permutation of variables that leads to a slightly better compression factor. But for practical purposes, let's say that the average scenario is good enough. Okay, so it's hard that you hit a permutation that is nasty and kind of derails you. Most of the times you are fine with a random permutation. And we were always happy with the backend in that sense. But it's a very good question. People have researched that.
All right, so this also seems like a quite general model. So do you envision other future applications where you could use maybe for other visualization tasks, a similar tensor train model as a backend for different tasks? Do you think it's possible?
Yeah, we have done it in the past. I mean, very shortly, I mean, we have done beyond the sensitivity task. We've also studied how to explore such models, not just computing Sobol indices, but doing other kinds of tasks that you can visualize even in a browser interactively. Haiyan, do you have any ideas or want to say something?
No, not really, but so as just in the talk, when we demonstrated this Ebola spread model, also if you see also, there's also a lot of other predefined models. So our application not only restricted to one or two applications, but lot of the, especially for like the simulation functions or mathematical models, physical models, if you fit into the predefined framework, then you can also upload your own function. And our system is also able to generate the Sobol indices, then analyze, and then you can explore and understand your model better.
And then I was wondering, so for the level of expertise that you expect your users to have, so for the current evaluation that you did, like, do you expect people to have a very detailed understanding of the mathematics behind this approach, or do you think even without this, someone would be able to use your tool?
For this, first of all, our application is not for very general use, so not like non-expert. You can understand under the explanation, you can understand how the system works. But to use the system, we are actually defined for especially the experts who need to analyze for example, they have a model, they have a function, they want to analyze parameters and the sensitivity indices of the function. Then for those experts, because they have already a deep understanding of the model, or they already know the mechanism behind the model, but they just don't know for the model itself, the sensitivity behavior, then in that case, our system or our product is very good for those specific uses.
All right, so let me check once more. So there's one comment from the Discord. So Renato says other kinds of problems similar to subsets and their scalar or multivariate output could be addressed in a similar form. So I guess that's a comment to my previous question. Yeah. Otherwise, I don't see many other questions in the chat at this point. And also, I think it's time to continue with the next presentation. So thanks a lot again for this very lively and detailed discussion. And now we can move on to the next presentation.
Thank you.
So now it is time to continue with our next presentation, which will be about the visual analysis of electronic densities and transitions in molecules. So this is a joint work of Talha bin Masood, Signe Sidwall Thygesen, Mathieu Linares, Alexei Abrikosov, Vijay Natarajan, and Ingrid Hotz, who are from Linköping University and the Indian Institute of Science, and it will be presented by its first author.
Hi, I am Talha. I will be presenting our work on visual analysis of electronic densities and transitions in molecules. This is a joint project between Linköping University and Indian Institute of Science. Atoms are made of a small heavy nucleus in the middle, surrounded by a large cloud of electrons. The location of electrons is described by atomic orbitals. The molecules are set of bonded atoms. The location of electrons in a molecule is described by something called molecular orbitals, which are linear combination of atomic orbitals. Within a molecule, the two important orbitals are the highest occupied molecular orbitals and lowest unoccupied molecular orbitals. And a transition or excitation is a result of absorption of photons. So during this excitation, electrons get excited from occupied to unoccupied orbitals. To capture one excitation, Martin proposed the notion of natural transition orbitals, which capture what got excited, which is represented by hole NTO, to where it got excited, which is represented by the particle NTO. The computation of natural transition orbitals is fundamentally done based on density functional theory, usually using software called Gaussian. Chemists study electronic transitions using natural transition orbitals. I demonstrate this using one example here. The example is of thiophene quinoxaline molecule. The molecule has two subgroups as shown in this figure. So the green subgroup is thiophene and the orange subgroup is quinoxaline. The hole and particle natural transition orbitals are shown on the right. The problem now is to study what charge transfer happens between thiophene to quinoxaline between the hole and particle orbitals. So usually the chemists use isosurface visualization for studying this problem. So they roughly say that the charge transfer happens between thiophene and quinoxaline because you see there is more charge density on thiophene in the whole NTO, and the charge density is less on thiophene side in the particle NTO. But fundamentally, we need a quantitative approach for this problem. So this is the problem we are going to address in this paper. We would like to mention that this work is in close collaboration with theoretical chemists. So two of the theoretical chemists are also co-authors of this paper. So in close collaboration with them, we came up with some visualization and analysis tasks for this problem. So we identified two analysis tasks. So one is parameter-free quantification of charges at atomic level, and the second is parameter-free quantification of charge transfer between subgroups between the whole and particle NTOs. We also identified three visualization tasks. So one is the visualization of whole and particle charges at atomic and subgroup level, and the visualization of charge differences at atomic level, and the third visualization task is the visualization of charge transfer between subgroups. Especially, we should be able to identify whether a transition is of local excitation type or of charge transfer excitation type. Now we briefly clearly define the problem. So we are given two scalar fields, one scalar field corresponding to the whole natural transition orbital and the other one phi p, which is the particle natural transition orbital. One condition these two scalar fields satisfy is that the integral over the whole volume sums up to 1. So that is the total probability of finding an electron within the volume is 1. Along with these two scalar fields, we are also given the set of atoms corresponding to the molecule and also the partition of the atoms into m subgroups. Now the problem boils down to determining the distribution of charges at atomic level, the distribution of charges at subgroup level, and also the charge transfer between subgroups, which is represented as a matrix shown here. We now describe the proposed pipeline. So we are given the atoms and subgroups as input in addition to the whole and particle natural transition orbitals. The typical method used for analysis of this data is to use isosurface visualization and to determine where the charge is moving among the subgroups. We instead propose a segmentation-based approach. So we compute segmentation at atomic level and then accumulate the charges within each segment to compute charges per atom at both whole and particle level. So this can be directly visualized as shown here. In addition, we also compute the charge transfer at the subgroup level. This we visualize using something called transition diagram. For segmentation, which is our analysis task 1, we use a weighted Voronoi diagram. And like we mentioned, we compute the charge per atom by accumulating the charge density within each segment. And then charge per subgroup can be computed by addition of charges per atom in the subgroup. We briefly want to mention what Voronoi diagram is. So Voronoi diagram is a partitioning of the space based on proximity to a given set of seed points. So for example, on the right, a set of seed points is given. For each point in the space, you compute which seed point it is closest to. So for example, the point P is closest to the point Pi. So it lies in the Voronoi cell of that seed point. We use a weighted version of Voronoi diagram. So here each point has additional weight associated with it, which can be represented as a radius as shown in this figure. We want to clarify our design decisions behind using Voronoi diagram for segmentation. So one of the key aspects is efficiency of this approach. The second thing is simplicity of this approach. It is easier to communicate to the domain scientists who are the ultimate users of this tool. And we also performed an exhaustive study comparing the Voronoi diagram approach with the gradient-based approach and found the results to be very similar. And you can also observe the segmentation at subgroup scale is quite accurate provided by the Voronoi diagram. Once we have computed the segmentation at atomic level and accumulated the charges within each atomic segment, we can visualize the charge distribution at atomic level both at whole natural transition orbital and at particle natural transition orbital. So we can see clearly that in the whole, the yellow sulfur atom had the highest concentration of charge, and in the particle NTO, the concentration of charge moves to the right side of the molecule, the quinoxaline part of the molecule. We can also visualize the difference between the whole and the particle NTO charges at each atom to observe which is a donor atom and which is an acceptor atom. In the visualization on the right, the red indicates it's a donor atom and the blue indicates it's an acceptor. Now we discuss the problem of the charge transfer, the second analysis task. So we are given two charge distributions, one at whole orbital and one at particle orbital. So now the question is how the distribution changes from one at the whole orbital to the particle orbital. So we have to determine one possible solution, which can be represented as a matrix, M by M matrix, where M is the number of subgroups. Each element in the matrix is the amount of charge transfer from the subgroup I to subgroup J. So note that the solution should satisfy some of the constraints. For example, the sum of the charges which is arriving at one subgroup should be equal to its particle subcharge, and the sum of the charges which is leaving the subgroup should be equal to the whole charge of the subgroup. We convert this problem to a simpler problem as follows. So we make some reasonable assumptions. So for example, the charge transfer should always be positive. The second thing is there is no charge transfer between two donors, which is very reasonable to assume. And thirdly, there is no charge transfer from an acceptor to any other subgroup. So these assumptions disallow following charge transfers. And also it forces the charge transfer from subgroup to itself to be the minimum of its whole and particle charge. So now the diagonals of the matrix are determined, and also the unknowns become fewer. So we have a smaller n by m matrix where n is the number of donors and m is the number of acceptors. And also in terms of the graph representation, the problem changes from unknown weights of a complete directed graph to a bipartite graph. We propose two solutions for the charge transfer problem. The first solution is called the proportional solution. So the charge distribution at whole and particle on four subgroups A, B, C, D is shown on in the image on the right. So based on our assumptions, we know that the charge transfer from the group to itself can be uniquely determined. However, half of the charge still is unknown. So first of all, we divide the subgroups into donors and acceptors, so which is here. So we know that group A has 0.2 charge, which is unaccounted for, and similarly the group D has 0.3 charge, which is unaccounted for. On the whole orbital, we have excess charge on groups B and C. Now, to determine the charge transfer between B to A, we can use the proportional charge transfer approach. So which is defined as take the product and normalize it with the total charge. The other approach for charge transfer computation is based on quadratic programming. So we have two donors and two acceptors, and between any donor-acceptor pair, we can assume that the charge transfer is same throughout. So we start with a matrix Tp, which has equal charge transfer of 0.125 between any donor and acceptor. But this matrix doesn't satisfy the constraints. The constraints are specified in the four equations below. So we find the closest feasible solution to our matrix Tp. So using this approach, we find the solution to be the matrix T is specified at the bottom right. Now we have computed the charge transfer matrix. We wanted to explore what kind of visualization approaches can be used for the visualization of this charge transfer matrix. We started with simple bar charts where we ignored the charge transfer between the subgroups and only showed the charge distribution at the whole and particle orbitals. This visualization was found useful by the domain experts, but they wanted to see the charge transfer between subgroups as well. So we used a chord diagram for representation. This visualization was not found to be very useful by the domain scientists. They found it quite confusing to begin with. Then we switched to Sankey diagram based visualization, which was found to be very useful by the domain scientists, and they preferred this visualization approach. So we used a modified version of Sankey diagram for visualization of charge transfer matrix. We call this a transition diagram. The transition diagram shows the whole charge distribution at the bottom and the particle charge distribution at the top. And in the middle, the connectors show the charge transfer between various subgroups. Note that this transition diagram is quite efficient way of capturing the nature of transition. For example, in state 4, there is a strong charge transfer character, and it is quite obvious that the charge is flowing between thiophene to quinoxaline subgroups, while in state 9, it has largely local excitation character, and the charge transfer happens between quinoxaline side of the molecule itself. We now demonstrate our pipeline using one of the case studies. So here we are given a copper complex, so which is shown on the left, which has one ligand fixed and the other ligand which is changing. So you can see on the right of each molecule the ligand is changing, while on the left the ligand remains the same. If you use the traditional approach of direct visualization using isosurfaces, so this is the result. In the middle row, we show the whole natural transition orbital, and at the bottom we show the particle natural transition orbital. We can examine each molecule individually, and then probably we can learn something, but we don't see any patterns here. Now we switch to our approach. So we show the segmentation at subgroup level on the top. So you can see the blue subgroup remains constant throughout. Similarly, the copper in the middle also remains constant, while we vary the ligand, the second ligand. So it is green on the first, then gray and purple and so on. Now at the bottom, we see the corresponding transition diagrams. Within the transition diagrams, we can immediately see what kind of transition it is. So largely the copper is losing its charge to one or both of the ligands, and the pattern immediately becomes obvious. So on the left, the two molecules, the charge flows from copper to both the ligands, while on the right, the charge flows from the third ligand and copper to the second ligand, which is the phenanthroline in the middle. To conclude, we proposed a pipeline for visual analysis of electronic transitions using natural transition orbitals. This pipeline is flexible, and each module can be replaced with an alternate approach as well. Also, this pipeline can be used for other applications, for example, analysis of crystal structures coming from material science domain. So the main takeaway is quantitative approach is better than qualitative isosurface-based visualization, which has been the norm in this field for so long. We also propose a transition diagram which captures the nature of the transition accurately, whether it is a local excitation or a charge transfer kind of excitation. The transition diagram also allows for identification of similarity and differences between different molecules. In future, we want to explore different alternatives for design decisions we use. For example, instead of geometric approach, we can use topological segmentation approaches. Similarly, during the charge transfer computation, we use an optimization setup. Here, we want to introduce additional constraints based on geometry and topology, etc. Further, we want to explore ensembles of molecules and do automatic classification of electronic transition. Lastly, we want to acknowledge the funding from VR and CERC. Thank you very much for listening to this talk.
So hello, and thank you again for your very informative presentation. So now let me start maybe with one question. So I think the visualization that you're creating, it's very clear and intuitive. And part of the strength derives from an abstraction that you do. So rather than showing the isosurfaces, you assign the charges to the individual atoms in the molecule. Now, I wonder if this level of abstraction, if it also introduces a little bit of uncertainty, because maybe in some cases, we're not quite sure where should a certain charge go, which atom should it be assigned to. Do you think it would make sense to try and capture this and visualize this maybe in a future version of your approach?
Yes, absolutely. So you are completely right. So for example, the segmentation depends on what kind of atomic radii you are using. So if the radius has some uncertainty, the segmentation will also have some uncertainty. And actually, right now, we are kind of working on something of a related problem. So where we are looking at multiple transitions simultaneously and trying to come up with a summary representation of multiple transitions. So that also requires representation of some sort of uncertainty or mean value along with some variance. So how do you capture that? So we are kind of working on this problem right now. Yeah.
Very good. So then there's lots of applause also for your very nice presentation on Discord. So I would also be interested in the second task that you're tackling with the charge transfer. So there you had to make several simplifying assumptions.
Yes.
So there it wasn't quite clear to me, were you mostly forced to make them for computational reasons so that the problem became tractable? Or is there also some, say, physical justification where you can assume that these assumptions, they are simply safe to make and we're not introducing any error there?
You are completely right. So it is a combination of both. So the problem itself, if you look at the original statement, so that is determining this M by M matrix, and we don't have enough constraints to determine that matrix based on those constraints. So we have to make some assumptions. So even after making some assumptions, you don't have an exact solution even then. So that's why we propose two different solutions. So one of them allows you to have more control. So you can set some predetermined weights and you will get a solution based on those weights. The other is more direct, that it will give a single solution, but it's more of an heuristic kind of approach. So it is a combination of both intractability, how to solve it, and in combination with the inputs from our domain collaborators. So they were satisfied with the assumptions we made for this problem. Yeah.
Very nice. So for the visualization, probably it doesn't matter that much because you can do both the segmentation and the charge assignment and the computation of these charge transfer matrices. I guess you can do it all in a pre-process. But still, I was wondering, can you give us a rough idea how much effort is it? Like, does it take 1 minute or 1 day?
Okay. Yeah. So the most of the time, if the computation time is spent in the segmentation, which is the Voronoi-based segmentation, and that increases based on the number of atoms in your molecule. So for the systems we have studied, so we didn't go more than, let's say, 200 milliseconds for pre-processing stage. So you are right. Like if you have a very large system containing lots of atoms, and also the resolution of the grid you are computing on, that is also very large, then the computation time can be higher. But for our systems, it was less than a second.
Okay, so people can even interactively load in new data and start to inspect it right away. So then the final question from my side would be, so in the case study that you presented, you wanted to compare many different molecules and you just juxtaposed them side by side. So do you think it might make sense to come up or to extend this with some explicit encoding of the differences to get a better overview or to get a better sense what are the differences between similar molecules?
Yes, you are right. So you are right. So like I mentioned before, so this grouping of similar transitions together and how to represent and encode it in a nicer way. So that's a challenge. And we are working on it and hope to have results soon.
It's always good to have some ideas for future work. That's right.
Thanks.
So let me check one final time. I think it seems that there's nothing really urgent on Discord. So thank you again for your very nice presentation and for this engaging discussion. And then I think we can move on to the next presentation. So with this, we are ready for something completely different, namely the characterization of thunderstorms using visual analytics. So this is joint work by Alexandra Diehl from the University of Zurich with Rodrigo Pelorosso, Juan Ruiz, Renato Pajarola, Meister Eduard Groller, and Stefan Bruckner. And these 6 authors are actually from 7 different institutions. So in order not to take up all the time, I'm not going to read out all of them. Rather, I'm just going to leave the stage to the presenter.
Hi, everybody. Welcome to my talk. Today I will introduce to you Hornero, our work on thunderstorms characterization using visual analytics. Thunderstorms are among the most prominent high-impact weather events. They produce natural disasters such as extensive flooding, dangerous hail masses, and strong winds. During a thunderstorm outbreak, expert forecasters need to analyze in detail large amount of data, and frequently they have to work in a very short time to provide timely alerts. These big data may come from observation systems such as satellites, weather radars, weather stations, and the data sources provide with new information in the order of seconds to minutes. On top of that, relevant events may take place simultaneously at different locations over the same region of interest. Therefore, analyzing thunderstorms is a critical task in operational weather forecasting to avoid economic loss, to prevent disasters, and save lives. That is why operational forecasters need efficient tools to surveil, to quickly detect, prioritize, and issue warnings about potential weather hazards in a matter of minutes interactively on a daily basis. We have been working for several years in close collaborations with meteorologists and researchers from the National Weather Services and the Center of Research of the Sea and the Atmosphere in Argentina. Together, we found a gap between existing current weather forecasting and storm tracking systems and our forecaster needs. Although they have powerful tools for data analytics, they are lacking different levels of abstractions and topological visual features that can accelerate the analysis of thunderstorms and help forecasters in efficient decision-making. That is true in particular in very short-term weather forecasting, where they have many tools to visualize weather radar data and trajectories, but they need software that can integrate storm tracking results, radar data, and storm properties at different levels of abstraction. And all of that with enough simplicity to allow them making decisions in the context of very short-term weather forecasting, namely nowcasting. To fill this gap, we developed a visual analytics tool centered on our forecasters' task workflow. Their task workflow is based on the task workflow recommended by the Warning Decision Training Division of the National Weather Service in the United States, and it is adapted to the National Weather Services in Argentina. We identified key tasks that expert forecasters perform daily when facing a potential severe weather event associated with thunderstorms. The first task is surveillance of storms in operating weather radars. Then, the forecasters do a ranking of high-impact storms. Afterwards, further analysis of the storm structures and associated phenomena. And finally, the forecasting, the decision-making, and issue warnings of severe weather events. That's a key task. For that, we propose Hornero, our visual analytics solution for thunderstorms characterization. Our solution supports experts in these tasks: surveillance, ranking, further analysis, and forecast of severe weather events. We do that by means of visual features to overview storms and quickly identify high-impact weather events, a novel storm graph visualization to inspect and analyze storm topological changes and structures, as well as a set of interactive features for efficient identification of similar storm cells we name analogs. These analog situations are searched in a historical database used for very short-term forecasting. Before entering into the specifics of how our visual design supports forecaster tasks, we will describe the data sourcing use. Hornero currently uses two main data sources: radar data coming from the next generation radar, NEXRAD stations, provided by the National Oceanic and Atmospheric Administration of the United States, the NOAA, and structural information of storms detected by TITAN, a thunderstorm identification, tracking, and analysis and nowcasting system of the National Center of the Atmospheric Research of the United States. In TITAN, a storm structure is described as a raster object composed of connected pixels in a weather radar image. TITAN uses minimum and maximum intensity of the reflexivity as a thresholds to identify a storm object and model it as an ellipse. We refer to this as a storm cell. Once the object is defined, it calculates several geometric characteristics like the position of the centroid, its area, and orientation. In our solution, we model a storm cell as a change in a graph structure and save all of their available associated properties as provided by TITAN. We designed our solution with the goals in mind of being expressive, easy to use, and effective to prompt analysis and quick decision-making in the context of nowcasting or short-term operational weather forecasting. Each of our decisions was made in a participatory design process together with our domain experts. So I will now walk through those design choices supported by their task workflow. In a surveillance task, forecasters first need to overview the horizontal distribution of the radar reflectivity and then to analyze other derived properties. So to assist them in this task, we designed a map overview showing the latest radar data and the latest detected storm cells. We choose this map visualization because storms are inherently spatial, and our experts are highly trained in spatial visual analysis. They can quickly identify changes on the map, make rough estimations of distances between 2 points in the map, between 2 storm cells, or time steps, for example, to identify rapidly growing storms, and in this way reducing the cognitive load needed to perform this task. We also provide them with a focus plus context interactive features that allows them to show the contour lines corresponding to this complete storm evolution as contextual information. On top of that, forecasters can add other properties such as volume, cell volume, hail, intensity, and many other properties as new layer on the map. By this means, they can overview at a glance the complete storm development. As a next step, forecasters rank different storm clusters depending on their severity. To help the users to detect relevant information, we provide them with a multivariate visualization tool that shows the different characteristics and allows the users to do a compounding analysis between different variables. For example, here we can see that the user selects and filters properties associated with potential dangerous storms. For example, large cell volume and high intensity. After this step, the user can do further analysis of spatiotemporal features and topological changes on the storm structure. For that, we designed two complementary views. First, a trajectory view that shows the different storm branches, reveal turning and splitting and rejoining of the storms, as well as a storm graph structure that is an abstract visualization that can reveal topological changes in the selected storm cells. For example, in this case, the storm cluster presents three branches, with bifurcation into the northeast and southeast branch that leads to the development of high-altitude storms that are associated with potential dangerous events. We adapted the graph layout to easily identify storm branches that are geographically close to each other. This is especially helpful when the storm structure is large and contains multiple branches coming from different geographic areas. We added an interactive feature to this graph that provides the options to collapse consecutive time steps into a single glyph, reducing the clutter in the graph displayed. We developed our visual design with a focus on simplicity and aesthetics, provided by the Gestalt laws of proximity by means of geographically clustering layouts, similarity by using similar color encodings, and continuity by adding the interactive collapsible features. After all of this analysis and to complete the task workflow, forecasters now cast and issue short-term warnings about potential severe weather events. Currently, there are two groups of operational techniques that can be used and combined to provide forecasters with adequate guidance for issuing short-term warnings. These are numerical prediction and, on the other hand, data-driven prediction systems, also known as nowcasting. Nowcasting uses the latest weather radar data to predict weather events in the range of minutes to a few hours, up to 6 hours. We designed a first visual approach for assisting our experts, operational weather forecasters, in nowcasting. We wanted to enable them to evaluate how likely is that the current storm cell will develop into a dangerous phenomenon, based on the pronto analysis of similar situations in the past we call analogs. So, to support this critical task, we developed a visualization component named the analogs view. We define an analog to a current storm cell, let's say I, as a previous storm cell, let's say J, that is similar to I to a certain threshold. For the similarity measure, we adapted the algorithm provided by Shai al, you can find in our paper, named Saldeda, and defined a weighted function using Titan's output, calculating a weighted difference of volume, difference of area, longitude, eccentricity, and amplitude. Afterwards, we calculated the probability distribution for each available property as it comes from Titans among all analogs and visualized it by means of a histogram, which is a simple visualization that is familiar to our domain experts. We use the same color encoding as the color encoding used for each particular property, and the bin containing the property where the current storm in analysis appear is indicated also in a shaded texture bar. To evaluate our system and design choices, we performed 2 rounds of semi-structured interviews with expert meteorologists at National Weather Services in Argentina. All of them with more than 3 years of experience in operational weather forecasting. And one of them actually is the head of the operational forecasting team at the National Weather Services, and has a strong experience in operational workflow, which was very interesting to us because we wanted to model their workflow. Two of them also work as operational forecasters, and the other two are researchers working at the National Weather Service as well. So the results of our interviews showed that domain experts found the visualizations very to extremely expressive, very easy, and also moderately to very effective. These very positive results were not all. They also proposed the scenarios where our visual tool can work. For example, to perform real-time analysis and post-factum analysis, to monitor the meteorological situation and carry out analysis of the severity potential, and finally to estimate the near future displacement of thunderstorms in between a particular region. After analyzing the very positive results of our interviews cycles, we summarized some lessons learned. For example, our results reinforce the ideas discussed during the application spotlight session in the Visualization in Meteorology and Climate Science session at the EuroVis 2019, where one of the main claims was that more tailored and user-centered, domain-focused approaches for visualization systems or weather forecasting are needed. On top of that, we also conclude that visual design for quick and high-impact decision-making over large datasets requires user-centered, intuitive, expressive, and low cognitive load, yet effective visualizations. So we will continue working in this area, and a next challenge for us includes working with the additional datasets and formats that can be useful for our domain experts and integrating Hornero into the domain expert current tool set. We are looking forward to do more research together and user studies. With this, we thank you for your attention and we look forward to your questions. Thank you.
So first of all, thank you a lot for this presentation. It's clearly a highly relevant problem and also a very sophisticated visual analytics approach to it and very nicely presented. So thank you.
Thank you.
I also want to remind our audience to please remember to put the questions that you might have on Discord. But maybe I can start with one. So one thing that I also really liked about your work is how closely you interacted with the domain experts. And you showed in the end that they really liked what you did. But now I'm wondering, did they also bring maybe a wish list of future extensions, features that should still be added in the future?
Right. Well, this is a highly timely problem, right? And the tools are getting, nowcasting tools are getting better and better. And moreover, because of the amount of data that we have available, especially with the new nowcasting tools, as I mentioned in the presentation, and it's mentioned in the paper, based on data-driven tools, based mainly on radar data. So they are working currently not only with radar data but other data sources, and this is a big challenge. So they have a wish list, including the integrations with their current tools, to have one way of access to such a diverse of information. They are also working with other kind of unstructured data sets, such as social media, and so to monitor weather events. So this is something that they also need. And the future step, of course, for this, it's to do a climatological analysis to understand how well the analog techniques can perform.
So now indeed we have questions coming in from the audience. So the first one is by Helmut Dolaisch, who first says, thank you for the great presentation of this very interesting and important work. From previous work we did with severe weather warning researchers, we got feedback that 3D structures of weather radar data is very important to analyze, to be able to predict and short-term forecast severe weather conditions, such as, for example, the building of hail. Do you plan to also include 3D visualization? For example, volume data visualization for the 3D radar data sources, so that this can also be assessed?
Yeah, thank you, Helmut, very much. That's an excellent question. And really it's very challenging, I know. So I've been working with weather forecasters and meteorologists and researchers since 8 years already. And that was the first thing that we discussed back in the time. But the problem is that is to encompass 3D visualization with nowcasting, which is the forecasting in the range of seconds to 6 hours. And so there are excellent work also done in, for example, Met3D, and so from our colleagues from Germany and so on. But how do we customize this or tailor this to decision making? That's an open question, in my opinion.
Mm-hmm. Okay, so maybe a out of the box volume rendering, you're saying might
Yeah.
you definitely need something more, maybe a novel visual design for this.
It's a challenge. I don't see an answer to this at the moment, but definitely because of the size of the data, it's a gigantic data set. Maybe the solution comes from progressive 3D visual analytics.
Mm-hmm. Then there's another question by Sylvia. How do you tackle temporal and spatial uncertainty in the data as well as in the prediction?
Mm-hmm. So this is so in decision making. So to communicate uncertainty in the context of decision making, it's a challenge as well. Thank you, Sylvia, very much for your question. I saw it coming, and it's at the moment, we give them the tools, for example, with the visualizations of the histogram visualization of the analogs, so they can make quick decisions so by using the pre-attentive and very familiar tools. So they make the decision, so they see the data as it is. So the probabilistic, the PDF, the probability distribution function would be the way we show the uncertainty there. And they are trained for that. But this is also future research. There are many other places where we didn't show uncertainty, such as the trajectory visualization of the graph visualization. I don't know.
Okay, so this decision making based on the analogs, I think it's a quite interesting idea, and it has a certain similarity with just KNN, K nearest neighbor based classification, which is somehow an automated technique that automatically considers the most similar instances that have happened in the past. And then very quickly, automatically, objectively, it would compute a probability of the outcome based on this. Mm-hmm. So do you think the experts can give you a more reliable assessment than such an automated computation of a probability?
Yeah, it has some, you're right, it has some similarities. The way of providing robustness, so they need an objective. The answer is they need objective validation. So they are going to go with automated analysis, definitely. That's based on climatology. So that means if there is some subjectivity in the data, it's very hard for them or they will not take it as valid at all. So they will go for an automated methods. What we have applied an analogs technique in other contexts, and the way of ensuring the robustness is to use skill scores based on 30 years, or there are papers with 10 years of database of previous data, previous observations coming from radars, and adjusting, I think, the KNN, conditions, so the season and the spatial area where they do the analysis. Yeah. So.
Right. So thank you very much again for this quite detailed discussion. Now, unfortunately, even though I would very much like to continue it, it's time to move on.
Mm-hmm. If may I say,
yeah, sure.
Very quickly, I wanted to thank my collaborators. It's a big group, and it's a lot of fun because all of them come from a very complementary background, and the brainstorming, it's really just amazing. And I fully recommend it to work with this collaborator.
Okay, so in this case, I'm not just going to thank you, but I'm also going to thank all the co-authors of this work.
Thank you.
So last but certainly not least, we have a work on a modified double gyre with ground truth hyperbolic trajectories for flow visualization, which is by Steve Wolligan, Thomas Wilde, Christian Rössel, and Holger Teisel from the University of Magdeburg. So I'm looking forward to this.
Welcome to our talk about a modified double gyre with ground truth hyperbolic trajectories for flow visualization. I will talk about hyperbolic Lagrangian coherent structures and especially their boundaries, about a model of a double gyre, and of course about our modification of it that has a closed form solution of a hyperbolic trajectory. At the end, we will check if two boundary extraction methods are working correctly with help of our modified double gyre. The analysis of hyperbolic Lagrangian coherent structures, or short LCS, is a standard problem in flow visualization. LCS describe coherent masses like water or air in a flow. For example, this yellow region here is clearly distinguishable from its neighboring areas, or also this blue area here. And with these distinguishable areas come these boundaries. A lot of research has been done to be able to extract these boundaries. Most of the extraction methods are based on the flow map gradient, which is known to be numerically unstable, and that's why it's hard to compute the exact positions of a LCS boundary with these methods. Now, what is a double gyre? A double gyre is a flow pattern that frequently occurs in geophysical flows. In 2005, Shedden and colleagues introduced a simple model of a double gyre. It was cited more than 1,000 times, and we estimated more than 100 that use this benchmark dataset for extracting LCS boundaries. The model is an analytical unsteady vector field V defined as the cogradient of psi. Psi is here, and psi is defined in the following way, and it comes with 3 more equations. The double gyre has 3 user parameters, A, epsilon, and omega. And yes, this equation is relatively simple. And yeah, what does it look like? Here you can see streamlines of the double gyre, or streamlines of one time step. These streamlines show 2 gyres, this left one and this right one. And these streamlines are shaped like circles, and we have this boundary here in the middle, and this boundary moves periodically over time from left to right and back. And yeah, these are the streamlines for different time steps. And now we can see path lines. These path lines define trajectories of particles that move in the flow, and they quickly become relatively complex, and at some locations nearby particles tend to move apart from each other after a certain time. And where does this happen? This happens exactly at these LCS boundaries. Now let's take a look at an example. If we place 2 particles very close to each other, but one is on the other side, on one side, and one is on the other side, and if we advect them, they stay relatively long together, and at some point they move away from each other. And yeah, this defines such a LCS boundary. And unfortunately, there is no ground truth solution of this LCS boundary. That means it has to be computed numerically, for example, with FTLE. What this is will be explained later. George Haller developed another approach. He says the key to computing 2D hyperbolic LCS boundaries are hyperbolic trajectories. Those hyperbolic trajectories are special path lines that have maximal hyperbolicity. And this means that such a path line, each position of it has to be in a hyperbolic region. These hyperbolic trajectories act as origins of LCS boundaries. And this is why it's the key to extract or compute these hyperbolic LCS boundaries. And one way to extract those hyperbolic trajectories is with FTLE. Now, what is FTLE? FTLE is a scalar field that describes the amount of stretch of surrounding particles. Here you can see in blue regions where the FTLE field has low values. Green are intermediate, and these yellow ridges here have a very high value. And blue means that particles that are seated here relatively close together will also stay together. And at those yellow regions here, these particles split away from each other after a certain time. That means that most of these ridges of this field describe hyperbolic LCS boundaries. There are also other ridges that do not describe LCS boundaries, and I will show this later. This method is based on the flow map gradient, which means this is maybe not the best method. In the following slides, we will use an extended domain of the double gyre. The analytical description of the double gyre results in LCS boundaries that continue in the region below the actual domain. And as you can see, there are two more gyres that share the same location of the moving boundary between the actual two gyres. Now, how can positions of hyperbolic trajectories can be extracted with FTLE? First, we need to compute forward FTLE at some time. And that means we need to eject particles forward in time to get this field. And again, in yellow, you can see regions where particles split away from each other in forward time. And you can also compute this for particles that get ejected backward in time. And also here, yellow means that particles move away from each other in backward time. Now, if we superimpose those two fields and check for intersecting ridges, these hyperbolic trajectories can be extracted if some properties are fulfilled. As you can see, there are several intersection points here, here, and here, for example. But only one of those intersection points fulfills the requirement to be a hyperbolic trajectory or a point on this hyperbolic trajectory. And exactly this point is the key to understand the double gyre field. If one would know the exact position of it, one could extract LCS boundaries with only the coast of a flow map evaluation and not of its gradient. Here we can see a space-time view of the double gyre domain. This means that time is treated as if it would be a spatial domain. Time grows in this direction. In blue, you can see the stable manifold of the hyperbolic trajectory that is a stream surface that represents a set of streamlines. And the red line represents a LCS boundary. A LCS boundary at some time step can be computed by extracting a slice of the stable manifold at exactly this time. Here you can see 3 slices at different time steps. And you can also watch the LCS move as time changes. This means that if one would have an exact solution of the hyperbolic trajectory, an extraction of a LCS boundary only depends on the flow map that is numerically much more stable than its gradient. Unfortunately, this position of the hyperbolic trajectory does not coincide with the position of the nearby saddle-type critical point, which is shown in red. This one's the position of the hyperbolic trajectory, and they do not coincide. The position of the hyperbolic trajectory seems to move in a sine-like function, but unfortunately this is not the case. There is no analytical solution to describe this hyperbolic trajectory. But we can do something and modify this double gyre to define a sine-like hyperbolic trajectory. And yeah, now here comes our idea. The modification should fulfill these two requirements. It should have a ground truth hyperbolic trajectory in a closed form, which allows for computing LCS boundaries by numerical particle integration, and it still should be close to the original double gyre. Our solution is a reparametrization of the temporal domain of the original double gyre. That means we introduce this p. The hyperbolic trajectory is described by this sine function g. You can see g in the picture again as a green curve. Now we have to define how the reparametrization p should look like. It should be rather small, because the smaller the reparametrization of the modified double gyre, the more similar are the original and the modified double gyre. And it should have the same periodicity, of course, as the original double gyre, and it should ensure that g is a hyperbolic trajectory of the modified double gyre. Let's first take a look at the last criterion. A hyperbolic trajectory is a special path line, so let's first make sure that g is an actual path line of our modified double gyre. In general, a path line is a tangential curve of a vector field v. That means the derivative of p at some time t has to be equal to the vector of its corresponding vector field at the position p of t and at time t. Yeah, we can plug in our g and v bar, where v bar is the reparametrized double gyre. And now we can solve this equation, we can solve this equation for p. And fortunately, there is a closed form solution which looks like this. That means that g is a path line of the modified double gyre. Now we can check if the path line g has the special requirement to be a hyperbolic trajectory. The requirement is that it needs to have maximal hyperbolicity. That means that each point of g needs to be in a hyperbolic region. A point is located in a hyperbolic region if the determinant of the Jacobian at this location has a negative determinant. The Jacobians of our line, or on our line g, can be described in this way. And it can be shown that all Jacobians on the line g are of this form. That means that the Jacobian is negative h squared, which is guaranteed to be negative. This means that g is not only a path line, but it's a hyperbolic trajectory. Now one last thing needs to be done to have the final vector field that defines the modified double gyre. We need to specify the constants c and d. But how do we do this? We need to require q to be as close as possible to a sine curve with periodicity 10. That means one time period of our modified double gyre has to also be of length 10. And we do this by setting a maximum of 1 at location t equals 5 halves. That means we need to set q at 5 halves to 1 and the derivative of q at 5 halves to 0. Unfortunately, there is no analytical solution for this, and that's why we need to find a solution numerically. And this is the solution. And with this, we have set up our approximate value for C and D, and we are done, and finally have our reparameterization P. Now let's look at how decent the reparameterization actually is. This animation shows again the space-time domain of the double gyre. The black lines, this one, and this one, show one period which has a time range of 10. As you can see, the reparameterization of time is very decent, and you can only see it in direct comparison. And this is a combined view of the FTLE fields of the original and our modified double gyre. The red ridges belong to the original one, and the blue lines correspond to our modified version. As you can see, the ridges differ only slightly, and that means that both our goals are achieved. The difference is minimal, and we have a description of the hyperbolic trajectory as a closed form. Now we can use our new benchmark dataset to check if some LCS boundary extraction methods are working correctly. The first example we tested is a work by Wilde and colleagues that extracts FTLE ridges for long integration times. Again, extracting FTLE ridges is difficult since it's numerically unstable. False positives can appear, and there can be extreme gradients. Wilde and colleagues track FTLE ridges by increasing the resolution in regions where ridges evolve over time. In comparison to our ground truth solution, there appear gaps in the extracted LCS boundaries. This is our ground truth solution, and for example, here are missing some arcs which are present here. And as you can see, there are those crossing lines here which cross the LCS boundaries, and these are not present in the ground truth solution. And here comes the second method we tested for correctness. Machado and colleagues developed a local approach that extracts hyperbolic trajectories by relating them to 2D space-time bifurcation lines. Since hyperbolic trajectories are path lines, initial line candidates have to be optimized to become path lines. Candidate lines are lines where the acceleration or the jerk vectors can vanish. Here is an animation of the incremental optimization. You can see the xt plane where the hyperbolic trajectory is located at. In orange you can see the initial candidate line where the acceleration vanishes, this is here. And in violet you can see the second candidate line where the jerk vector vanishes. Our ground truth hyperbolic trajectory is shown as screen curve in both views. And as you can see, the orange line converges quickly to the ground truth curve, but the violet line does not. But since only one of the two candidates needs to converge, the method by Machado and colleagues is working correctly in this case. We constructed a second vector field with known hyperbolic trajectory. The time grows in this direction, and as you can see there are 3 disks. These 3 disks show superimposed forward and backward FTLE fields, and there is only one intersection point at each time step, and the ground truth hyperbolic trajectory successfully passes through the intersection points at each time step. In orange and violet you can see the initial candidates that need to be optimized for this second field. These are pretty far away and have a rather different shapes as the hyperbolic trajectory. And now when we start the optimization, you can see that the candidate lines seem to stay in local optima. For example here, it doesn't move anymore. And additionally, there appear some disturbances that get transported along those lines, and, which are this zigzag thing. This means that the method by Machado and colleagues unfortunately does not find a correct solution of the hyperbolic trajectory. And yeah. Now, to conclude our talk, we developed a benchmark dataset with ground truth hyperbolic trajectory for evaluating LCS boundary extraction methods based on the model of a double gyre by Shedden and colleagues. We have shown that simply a small reparametrization in time is necessary to be able to compute a closed form of a curve that represents a hyperbolic trajectory. And we have shown that LCS boundary extraction methods can be evaluated with our benchmark dataset that is suitable for use in future work. Okay, that's it. Here are the sources. Thank you for your attention, and now I'm open for questions.
So first of all, thank you for your presentation. I think for some non-trivial concepts, you had some very helpful illustrations and animations. And also, since this worked very well for the previous talk, I want to remind everyone again to please put your questions into the Discord chat or in the YouTube chat. But maybe I can start with one question. So since I'm not that familiar with the field, so you mentioned that this double gyre that you built on, that you're refining, it has 3 parameters. So can you give me a brief intuition what these user steerable parameters, what they do?
Yeah, that's. I have to think. So one tells how long this period is, and the other one is how far this centered boundary moves, and I think the third one is how fast the field at all is moving.
I see. Okay, so they have a quite intuitive meaning for
so it's no black magic.
So then, to me, it seemed like the take-home message is from the final evaluation that the existing methods that people have come up with for extracting Lagrangian coherent structures, none of them are fully reliable. Did I catch this correctly?
At least those 2 do not work in all cases.
Yes.
I don't want to say that every method that was developed is wrong now, but our data set is a useful help to check if these extraction methods actually give true results or correct results.
So do you have some intuition what is somehow missing in the existing methods so that they could produce more reliable and robust results?
Well, I don't know of all of the extraction methods, but so the main problem with FTLE is that so you for 2D you integrate 4 particles, and they can stay together if you would reparameterize those path lines. So they just shearing away, even if they are actually still together. And that's the problem why those crossing ridges are appearing at FTLE fields. So this is one major issue with FTLE.
Mm-hmm.
And yeah, I don't know. Yeah, I think there's always some minor problem. I don't know.
All right. Now I'm getting one question from the chat from Lutz Hofmann. Would it be possible to construct datasets with ground truth that are aperiodic in time, that are not periodic?
A good question. I would think more than 5 minutes about that. I guess. At least it is. I would say it's easier if you have a data set which is infinitely long in time, so that you don't have any discontinuities in time. cannot answer this question.
Okay, it's fine. It's probably not a trivial question. It requires a little bit of future investigation, but
Yes,
it could
right.
be some inspiration. And similarly, Ingrid Hotz has a question about a potential extension. So she says, it is always great to have data sets with ground truth. Do you have any ideas about how to generate similar data sets for three-dimensional flows? So that's another way of extending it.
Yeah, so for 3D, you would those boundaries are planes or surfaces, and that's why you would need to have a ground truth surface. Yeah, I also have no idea.
All right, so another interesting direction for future work. And since right now, it seems like there are no more urgent questions from the audience, I think I can thank you again and also all the other speakers from the session. Of course, now I think next up, we have a 20-minute break. And during this, also feel free to continue the discussion on Discord and Topia. So this is a big advantage that we now have, that we are not limited to this very short time that we have after the presentation, but you can continue the discussion afterwards. So with this, thanks again, everyone who participated, the speakers, the people who asked questions. And I really hope that I'll get the opportunity to see all of you in person again next year.